So when we are looking at electron configurations for ions, the important key is to think about how many electrons it has after losing or gaining the electrons to have this charge. So in this case, I've focused just on positively charged cations. Obviously, we can do this for anions as well. Each positive charge is one fewer electrons than we will have in the ion than in the atom, and each negative charge is one extra electron that ion, in that case anion, has, which the neutral atom would not. So with calcium plus 2, we find calcium recognizing it has 20 electrons, but it's going to lose 2 electrons. So we can think of that and just write the electron configuration for 18 electrons. 1s, 2s, 2p, 3s, 3p. But especially with our main group elements, our non-transition metals, it is going to lose electrons or gain electrons to become similar to or to have the same number of electrons as the nearest noble gas. That is the most stable ion that most of these things form, but that doesn't mean that that's the only thing you could ever be asked about. We could be asked about calcium losing 1 electron or 2 electrons, or nitrogen just gaining 1 or 2, even though it most often does gain 3. So make sure you're really looking at the charge, but we're also recognizing here we're losing those ones that the nearest noble gas doesn't, or if we were writing a noble gas notation, we're losing the ones that are beyond the noble gas. That has implications in terms of the size of the ions, the reactivity, and other patterns that we'll see. When we have transition metals, most transition metals we would describe as having 2 valence electrons, with a few exceptions. And we looked at chromium before, that doesn't completely fill the S sublevel. But as we start across a row, we first fill either the 4, 5, 6, or 7 S sublevel before we would start to fill our D or our Fs. That means the highest level, and I mentioned this in an earlier video with lead, the highest level up here is level 6. For iron, before it lost any electrons, it had 1s, 2s, 2p, 3s, 3p, 4s, then 3d. Yes, the D fill after the 4s, but because the 4s are at level 4, a higher level, a higher average distance, and there's lots of different technical terms we can talk about the difference between location of electrons, but really we're just thinking the highest level here. So iron, along with many of the transition metals, will likely form a +2 ion. In doing so, it loses the S electrons from that highest sublevel. But iron also forms a very common and very stable +3 ion. So when we look at that, we're just losing from that next highest or next most likely place. And with iron, the reason that that happens comes back to something we've mentioned earlier with chromium, is that when it is in its full electron configuration, its ground state, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6, it would look like that. And that balances the attractions from the nucleus with the repulsions of the electrons together. Well, first it loses its 4s, but then when it's left like this, still that could be a possibly stable electron configuration depending what it's with, and something we'll see, but we've already defined maybe. Ionization energy is the energy required to remove an electron. So even though there's some repulsion here, it still takes energy to get rid of that and to make our ion. So we do want to remember that yes, we're minimizing repulsions, but even when we say something like francium wants to lose 1 electron or calcium wants to lose 2, it still requires energy. It later makes a more stable compound, but the losing process is a process that requires energy. We are taking something away that is attracted to the nucleus. For tin is right over this shoulder here, directly above lead. So it's got some similarities to this electron configuration. And I point out the similarities to lead because it's got electrons level 1, 2, 3, that's totally full. The 4s, 3d, 4p are full. my highest level, or as I go across the last row, for a neutral atom of tin, it would be 5s2, 4010, 5p2. When we are first introducing the charge of ions, whether this is in biology, in ICP, in Chem, we talk about +1, +2, +3, and often we call the carbon family plus or minus 4. That's a simplification, and what can really happen is often much more complex. Tin and lead specifically, so if we jump up here, the electrons farthest from the nucleus, therefore most weakly held and easiest to remove, are in the highest energy level, level 5, and the p sublevel is further from the nucleus or less attracted to the nucleus than the s. So occasionally, or very often, lead and tin form +2 ions. But depending what they're bonding with, depending on those attractive forces, they can also form a +4. When tin forms that +4, it doesn't eat into that 4D. It still takes electrons from the highest level, level 5. So the equivalent up here with lead would be we'd lose these first, then these before we did anything with the D or F. Here on tin, we lose the 5p, we lose the 5s before anything happens to level 4. So the basics of this are patterns we may have seen before, but it is important to understand with transition metals how it is possible to predict the charges. But more importantly for us, it's possible to explain a charge. We aren't always asked to predict every possible ion that something can form, but if you are told it's forming a specific ion, that is something we should be able to connect to the electron configuration and explain based upon energy level and sublevel.